Hello everybody. Last lesson we have learned in chapter 5 about the centripetal acceleration, and if there is an acceleration, if you remember Newton's law, there has to be a force, and that's going to be the content of this lesson. So what we are going to have a look at is here chapter number 6. Dynamics of rotational motion. So first, as a small repetition, let's have a look at Newton's law. I hope you remember them. There were 3 laws, and we are just going to have, for the moment, to have a look at the first law. And what he said there was the principle of inertia, and basically it said that if you have no force, then the object remains on the move on a straight line. That was the first thing. At a constant speed. So, of course, you still knew that. So I'll just put a yellow box since it's nothing new. So let's now apply this to the circular motion. And we want to have a look at that. So we make 2 examples. The first one is here Earth and the Sun. So I assume you know that the Earth circles the Sun. So this is the Earth. And we do this circle. According to Newton's first law, the Earth is supposed to do a straight line if nothing happens. So basically the Earth should just follow this track if we have no force. So apparently we do have a force to make the Earth go round here, and this force is done by the Sun. Of course, this is the gravitational force that we know pulling the Earth and making the Earth go round. We can also have here a second example. For example, if you swing a tennis ball around yourself. So if this is you here and you take a string with an attached tennis ball or whatever else, and you make this tennis ball circle around you, then even there the ball is supposed to go on a straight line as long as least as we have no gravitational pull from the Earth that makes him fall down. But it goes around this circle. And what force is it that makes it go round? It is the force of this string. Or we could call that Ft the tension force, as we know. So in both cases we had a force towards the center that keeps the body on the circular move. And this is here the principle that we can state. To make a body follow a circular path, there has to be a force that is perpendicular to the motion. Let me quickly show this here. So we have, for example, here this motion, which is here along the circle, and the force is here perpendicular, and here the same. The momentaneous velocity is along the circle, so it makes here this a tangent, and it is perpendicular here this tension force. So that's the one thing, perpendicular and pointing to the center of the circle. So we could do a drawing illustrating that. So we have here a circular motion, and an object that, for example, at this position has the velocity in this direction. So it's just for this very short moment. So that's, for example, v1. Then the force has to point towards the center of the circle. So this is F1. And if later on the object is up here, the momentaneous velocity is along the circle. So it will point to this direction. Same magnitude, so it hasn't gotten faster, but a different direction. And the force still points towards the center here, F2. So if you go around this circle, the force always points to the inside, to the center. And although you have a force, the magnitude of the velocity doesn't change, but there is a change in direction. This force is sometimes referred to as the centripetal force. And a centripetal, centri is the centripetal, towards is given as, so we can just use here Newton's law, and then this F1, F2, F3 and so on is called for the magnitude Fr, R for because it's along the radius of the circle. And we can just use now Newton's law, the second one, which is F equals m times a, and we have learned that the centripetal acceleration is given as v squared over r, and therefore this is then m times v squared over r, or with the omega we can also write r times this omega to the power of 2. So this centripetal force is just a name, since it really has to be, so it's some sort of provided by a string or by gravity or whatever you have. So you need to have a real force that some sort of acts as the centripetal force and then causes the object to make this turn. I think we do an example with that, and the example is just what we had above: the Earth circling the Sun. So we know that it is one circle per year. So 1 year is then the period of it, and we can just now use this law. What force is needed in order for the Earth to do the circle it does? So there's a certain given radius, a certain given speed, a certain given period, and we can just get to the force. So we choose here this second formula to use, and we want to see what comes out. So we fill in what we have. So Fr is m times r times omega to the second, and we can fill in the mass of the Earth, 5.97 times 10 to the 24th kilogram. Then we need the radius, and the radius here is from Earth to Sun, 1 astronomical unit, as it is called, and this is some 150 million kilometers. So to be, that's enough, 1.5 times 10 to the 11 meter. And now we need the omega to the power of 2, and omega is 1 circle per year. So 1 circle, the angle is then 2 pi, and a year is 365 days times 24 hours times 3,600 seconds squared. Put that in a calculator. You can stop for a moment and see if you get the right answer. You should get something which is around 3.55 times 10 to the power of 22 Newton. Quite some force. But we know this centripetal force has to be caused by a real force, so to say, and we know what it is. It is the gravitational force. We have been looking at it quite quickly, and we will go through it in more details then in a later lesson. But the gravitational force is given as the constant g times mass 1 mass 2 over r squared, and we can fill in the numbers: 6.67 times 10 to the minus 11 Newton meter squared kilogram squared. Then here mass of the Earth we can copy from above, 5.97 10 to the 24th, and the mass of the Sun 1.99 times 10 to the power of 30 kilogram, and the radius also same thing as above, 1.5 times 10 to the 11 meter to the power of 2. And you can put this in the calculator and you will see that it is hopefully at least the same as we have gotten up here. So it has to be, and it will be, I assure you. So we have seen now that the centripetal force is given by this one, and it's just a name, and you have to have a real force like gravity that just causes an object to have a velocity on a certain distance or a certain angular velocity at a certain distance.